Hello and welcome to the Section 2.2 lecture today for our Bridges Math Probability class. Today we're going to be looking at kind of an overall goal is to look at some outcome counting strategies for when we have one event occurring and when we have multiple events occurring and trying to figure out how many outcomes are possible. We're going to be using tree diagrams as well as the fundamental counting principle. For our little explore activity that I want to start with, we're going to be rolling a die, rolling a single six-sided die 100 times and recording the result. So let me go ahead and take a look at that. It says here, what are the possible outcomes of each event of our experiment? So if we're going to roll a six-sided die, what are the possible outcomes? And you shouldn't be too shocked to realize that it's the numbers 1 through 6. And I encourage you to go ahead and give a guess for how many times you think each one of these values is going to show up. So the number of 1s you're going to get, the number of 2s, the number of 3s, and it's just a guess, but seeing as we're rolling 100 times, I would think you should probably make sure that your number adds up to 100. Okay. And take a guess. It doesn't really matter. For me, I think, well, maybe I don't get too many 1s. Maybe I only get 12 of those. I'm going to say, I don't know, probably 17 2s. 3s, I feel like I get a lot. Maybe I'll go with 20 of those. And so just a quick snapshot, I'm at 49 right now. So maybe we go 4s. Let's say we get 16 of those. And I think 17 of those. And so that's, I was at 49. Now I'm at 33. So I've got, that feels like, no, not 33. Yeah, 33. Hold on. Let's do this the hard way. Uh, 82. 82 overall, so I've got 20 or 16, 18 left. Sorry. I'm just going to go with 18 there. So that's my guess, okay? By no means do I think it's right. I just want a guess. So what I'm going to do is I'm going to pull up a random dice roller. I'm going to do it this time. All right. So we get 6. There's no good way to do that. No good way. 1, 5. And I encourage you to do this for yourself. And so far, it's feeling pretty random. A little bit weird that I got a 1 5 1 5 in a row there. But I'm not putting a whole lot of thought into it. I'm just rolling and writing. And you can either use this one, or I'm sure you can find some sort of app on a phone and do this one roll at a time. I know it's a little bit painful, but as we talked about last time, sure, I could do it just a couple times. I could do it, say, I just got done with 20, so I could do it 20 times and then multiply that by 5, but that's going to skew my results. And the thought that I put out there last time was I could also roll it once and multiply it by 100 times to say that I got 100 of that one number, but I don't think that would ever really be the case. I think the probability of rolling the same number 100 times is, I think that'd be tough. I feel like I'm getting a lot of 5s overall, a lot of 5s and 1s. And I guessed that I wouldn't get very many 1s. And I'm not seeing as many 3s as I thought I would. I said 20 of them would be 3s. Never once read it 2 very well. I don't know if I hit it that time. There's some more 3s. Notice one thing that I'm really not trying to do. I'm not trying to skew my data. I'm not trying to make it to where I hit something that I want to hit. So that's been 3 1s in a row, I guess. I missed one. What was that? 6. Guess that's another 2. I'm always kind of trying to see if the page refreshes, and it's not going too well. That was an attempt at a 6. Because I am worried at some point that this little random generator here is going to break down. But I don't know. And again, your numbers would be totally different than these ones. Obviously still using all the same numbers, but it's kind of part of the reason I'm not trying to make this look really good. I'm not trying to take my time with it, it's just taking a while. It kind of does. And you're doing something 100 times, so of course it's going to take a little bit of time. And there's only 6 possibilities, so you're going to get a lot of repeats, just like when we flipped a coin for heads and tails. There was really only 2 options. This one at least has some different options. Feels like I had more 2s in that column than any other number. Maybe I did, maybe I didn't. I'm almost there. Thanks for bearing with me. You probably could have skipped this and done it and then got to the end. Or maybe you're just rolling alongside while I'm doing it. I wouldn't be too sure that you couldn't beat me if you even started now. I don't know how long it would take to roll. I mean, I kind of do because all my classes today did it, but I don't really know how long it would take me just to roll dice and write it, but this feels like a lot having to go over here, then go over here. But we're getting there. We're almost there. Just a couple left. Here we go. Finish strong. Finish strong. 2 and last one. Another 2. I think it was. Let's see, come back. Oh, there's another 1 in there. Okay. So we'll call it that. All right. So then what I want to do is I want to count up all the different numbers that I had, and this will be what it'll be. I'm going to have to count them. I'm just going to go in order. So ones, I've got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Kind of lost count. I don't remember if 19 was that one or that one. I'm going to say 20, 21, 22. I'm going to say I had 22 ones. And if I end up off on my count, I'll know that it's probably the ones. Probably one too many ones, if anything. So twos wise, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that's supposed to be a 2. No, that's a 3. 10, 11, 12, 13, 14, 15, 16, 17. I had 17 twos. For my threes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16. Fours. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's like 15 fours. Fives, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I had 17 fives. And then the sixes. I don't feel like I had very many. But maybe I did. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Dawson Geyer,
10,
please
10,
report
10,
to the front
10,
of the
10.
school right now. Dawson Geyer to the front of the
11,
school right now.
12. Looks like I had 12 sixes. Let's see how we did on whether or not we got them all there. I bet I'm close. 99, oh no. So I'm guessing I probably missed a 1 actually. And whether I did or didn't, whatever it ends up being, we were close. Okay. Now this seems to be, I guess let me start off. This is my experimental probability from this simulation. All of these numbers show me my experimental probability of each event happening. You know, if we were to say what was the probability that and we would say experimental probability, that we rolled a 1, it was 23 out of 100, which is 23%. That's why I'm choosing 100, because it makes it pretty easy to figure out what your percentages are. Okay. We would expect, realistically, to get between 16 and 17 of each. So because I had that 23, I also traded it off with having not very many 6s, only having 12 6s. So overall, not bad. It gives me a look at some probability simulations, at some dice rolling stuff, and by thinking about the kind of expected value, if I had 100 rolls and I had 6 different categories, we would expect about 16.6 on each number. Each one is equally likely. That's the beauty of rolling a die. Okay. On to the main target of the day. I want to look at some ways of counting possible outcomes. So this, for the most part, is straightforward if we're talking about one event in our simulation, in our experiment. Okay, if I'm just rolling a 6-sided die, there's only 6 possible outcomes. If I'm flipping a coin, there's really only 2 possible outcomes. Now the question becomes, what happens when I start combining outcomes or combining experiments or trials? In this first one, we're talking about Miguel, who is going to select an outfit. He has 2 different shirts, tan and red, 2 different pairs of shorts, gray and khaki, and 3 different pairs of socks, black, navy, and white. And he just wants to make an outfit, and I kind of use the story that I feel like I go through almost every day, and I'm the first one up in my house, and I don't want to wake anybody up, so I don't want to turn on a bunch of lights, and find a bunch of clothes. My wife would be mad at me if I turn the light on. So I'm just kind of blindly grabbing at clothes and trying to figure out what to wear. So let's pretend Miguel's got a blindfold on and he's picking things to wear. He opens his shirt drawer and he can either pick the tan shirt or the red shirt. Okay, those are his 2 options. When he picks the tan shirt or the red shirt, it doesn't matter because he can wear anything with it. He's either going to grab gray shorts or khaki shorts. So we have gray or khaki and gray or khaki. It doesn't matter. And the way I kind of relate, or the way I kind of say this, is that the shorts don't know or care what color shirt you're wearing. You have an equal opportunity of grabbing either. And along the same lines, the shirt and the shorts don't care what color socks you wear. We have black, navy, and white for every one of these potential options. And it gets a little crowded here. And for some reason, this is much more crowded than before. Okay. So how many total possible outcomes are there? The ends of the branches show us all the possible outcomes. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 possible outcomes. And if I wanted to, I could say what they are. Tan, gray, black, tan, gray, navy, tan, gray, white, tan khaki black, tan khaki navy, tan khaki white, red gray black, red gray navy, red gray white, red khaki black, red khaki navy, and red khaki white. Now, having the possible outfits laid out like that makes the probability question a little bit easier. Because the next one asks, what is the probability that Miguel will select a tan shirt, gray shorts, and black socks? So the probability that he'll select tan, gray, black, that happens exactly one time out of the 12 possible. So that probability is 1 out of 12. The second question asks, what is the probability that Miguel will wear khaki shorts? So the probability of any combination that includes khaki shorts. And that's all these ones down here. Again, in this idea, we don't care about what shirt he's wearing, and we don't care about what socks he's wearing. There's 6 of those out of the possible 12. So that's 1/2, which we also could have determined by there were only 2 options for shorts, either gray or khaki. And so he had a 50-50 shot at picking either one of those. Okay. Now, sometimes, and I want you to add this, it's not really written in here. Sometimes doing a tree diagram is not the best way to go. This tree got a little bit too big for the space that I had for it, but it was still, relatively a small tree diagram. So sometimes we might want to talk about what's called the fundamental counting principle. Okay. The fundamental counting principle tells us that the total number of outcomes is equal to the number of outcomes, the product of the number of outcomes of each event. Okay. It's equal to the product of the number of outcomes of each event. In what we just did, for shirts, there were 2 possible outcomes. For shorts, there were 2 possible outcomes, and for socks, there were 3 possible outcomes. And so this 12 really comes from the 2 possibilities for shirts times the 2 possibilities for shorts times the 3 possibilities for socks. That gives us our 12. And the reason I bring that up is because in this next problem, a deli's trying to figure out how many sandwiches they can make. They have 6 types of bread, 8 types of meat, and 4 types of cheese. If we just look at what they can do with white bread, then 8 types of meat, let's say turkey, ham, roast beef, bacon, pepperoni, salami, steak, and chicken, you can see how my tree diagram, just for white bread, keep in mind there's 6 types of bread, 8 types of meat, and then for each one of these, there would be 4 types of cheese. And we have cheddar, Swiss, American, and blue cheese. This tree diagram is going to get ridiculous. So much so that I don't actually expect you to do it because you're not going to fit it here. Instead, we would look to use the fundamental counting principle to figure out how many combinations there are, to figure out how many different sandwiches they can make. And that comes from this. The number of sandwiches my pen's lagging, I hate it when that happens. Comes from the number of types of bread times the number of types of meat times the number of types of cheese. There's 6 types of bread, 8 types of meat, and 4 types of cheese. 6 times 8 times 4 ends up being 192 possible sandwiches. Okay, that would be a lot of lines in this tree diagram. So take that question off and go ahead and focus on the fundamental counting principle for that. For your practice, there's 4 problems down here. The top 2, I do expect a tree diagram, and the bottom 2 don't do a tree diagram. You'll see reasons why when you read through those problems. Otherwise, I hope you have a great day. Make sure you ask any questions you have. Get in touch with me and ask me those questions. Otherwise, have a great day, and we'll see you in class.